Immersive4Learning offers an innovative, intelligent educational platform that uses the powers of artificial intelligence, a 3D learning environment, virtual reality, and pedagogical models to improve teaching and learning in the enterprise and education sectors. Several aspects of the solution are highly innovative, incorporating the most current state-of-the-art technology. The VR content creation process is aided by the AI content engine, which assists authoring users in creating the virtual environment they want to use in the learning process. The suitable representation of the virtual space, its characteristics, and properties are all based on appropriate semantical and ontological models. New domain language for the virtual reality learning environment is being developed, which will be used semantically to describe all the aspects of the educational space, including graphical assets, their properties, types of possible interactions, domain knowledge present within the environment, and those skills which can be acquired. This learning environment is personalized to suit each individual student accessing the course, utilizing different parameters that evaluate learning progress while also employing available biometric parameters. To enable the evolution of the teaching strategy as the system is being used, AI continuous learning algorithms should be deployed, as opposed to conventional methods, which make use only of training data. Developing new, dedicated pedagogical models for the 3D and virtual reality learning environments requires new types of pedagogical strategies to account for different types of interactions and actions that can happen. Additionally, new methodologies are being developed to promote learning using associations, actions, or gamifications, which results in a much more engaging and efficient education process, increasing knowledge retention and reducing the time required to adopt new skills. When compared to other competitors in the 3D and VR educational domains, Immersive4Learning offers more advanced features and more innovative concepts, as well as provides a clear path forward with scalable and flexible architecture, enabling the simple addition of new components, features, and concepts. The table shows how some of the competitor companies stack up against Immersive4Learning, highlighting some of the most important features, such as the authoring process, personalization, pedagogy, and behavior tracking. As can be seen, the Immersive4Learning solution is a clear winner in this context. There are three distinct areas within the Immersive4Learning system where artificial intelligence algorithms are deployed. Firstly, the AI components based on decision trees are deployed within the authoring portal in order to assist teachers in the process of course creation. For example, based on the selected domain, the system can recommend the most suitable pedagogical strategy as well as the most appropriate virtual reality learning environment. This aspect is highly innovative, as current authoring portals are often very complex and not accessible to most teachers, leading to high costs and a lengthy process of course creation. Initially, template-based learning environments are primarily deployed, but at more advanced stages, domain language will be developed, enabling dynamic generation of the learning space. Secondly, AI components are used to track all available parameters and make assessments regarding individual student behavior, learning style, and cognitive performance, which can then be used for personalization purposes. The observed data include learning progress measures and actions, as well as any available biometric data, such as EEG or motion detection from face analysis. The algorithms deployed within these components include naive Bayes and feed-forward neural networks, with learning algorithms based on Levenberg-Marcotte optimization. Thirdly, AI-based decision trees are deployed within the pedagogical agent, implementing the teaching strategy previously selected. Based on the observed behavior, learning style, and cognitive performance, different personalization actions can be performed, such as prioritizing the type of educational content and the way that information is presented or requested. For example, using questions and answers or certain actions which can then be gamified. Currently, incremental learning is implemented, treating the observed evidence as new training data, but at later stages, continuous learning based on unsupervised algorithms will be developed, enabling the creation of new rules within the pedagogical model based on the observed learning performance. One aspect of the application of AI is the learning assessment of those students accessing the course using the web of VR-based technology. Essentially, the content is the same, providing the 3D or immersive space view of the same learning environment. During the course sessions, all the available data is collected, including the answers to those questions provided, the time required to complete each task, the preferred type of content accessed within the environment, as well as any available biometric data, such as EEG and face snapshots obtained from web cameras. Additionally, at later stages, more sophisticated biometric data may be available based on audio input and movement patterns within the virtual environment. This audio data will be multilingual, supporting different languages such as English and Mandarin. The underlying principles and algorithms will remain the same. Once all the data is collected, the AI engine is deployed to evaluate behavior, learning style, and cognitive performance, all of which are important elements in the decision-making process of how to personalize the learning environment in order to most effectively achieve the learning goals. As previously mentioned, the algorithms deployed represent an innovative approach when compared to the competition, as these methods combine biometric data and the analysis of learning in the three-dimensional space, utilizing a wider spectrum of observed parameters. Once the student profile data is available, namely, information regarding behavior, learning style, and cognitive performance, the digitized pedagogical model using decision tree-based AI makes a decision on how the course should progress. This process involves various components, such as the offering of particular additional help, the changing of the content type of the educational material, or the requesting of further actions so that the current skill can be mastered at the satisfactory level. During this process, the learning environment is appropriately personalized. In early stages, by administering more or less relevant educational content, but at later stages, using more sophisticated methods based on the domain language for the dynamic creation of the learning environment. Based on learning outcomes, the pedagogical strategy is appropriately adapted based on the inclusion of new evidence, not relying solely on the training data set. Currently, only a discrete set of rules are included, but looking forward, unsupervised continuous learning algorithms will be available for creating new rules which have not been previously taken into account. Such strategies stand at the cutting edge of science and are completely innovative when compared to existing systems and approaches. The following part of the video will provide a demonstration of the real system setup, including 3 students and 1 teacher in the classroom. The classroom in this case is just for demonstrational purposes. It can be completely virtual, with the students and teachers at geographically different locations. 2 students will be using the web-based interface to access the course, and 1 student will be relying on the HTC Vive VR head-mounted display and associated controllers for immersion into the virtual reality learning environment. The demo shows the students wearing the EEG sensor and allowing the laptop web camera to record their faces. The teacher and the students access the Immersive4Learning platform through the login or registration page. Once a profile is created, the system can be accessed using the appropriate access rights and roles. When the teacher is logged in, the page with the list of currently completed or partially completed courses is displayed, indicating the most important details of each course. The individual course can be made active or inactive, can be edited, or a completely new course can be created. For the creation of a new course, the Add Project button is selected, and the teacher is taken to the course view page, where first the main details need to be specified. Once this is done, the system recommends the most appropriate pedagogical strategy and virtual learning environment for the selected domain, topic, and subtopic. Some of the virtual learning environments can include multiple scenes. Uploading new learning environments or integrating external ones from the market is also possible. Furthermore, details related to the platforms used and personalization aspects can be specified. The selections are made according to the availability of the appropriate equipment, as well as the permissions to use biometric data. When the existing course is being edited, all the previously specified details are retrieved and shown in the Course View tab. Additional changes are possible in any part of the subsequent course creation process. Provided that the virtual reality learning environment is selected, the VR Environment tab is used to define how the graphical content is connected to the domain model. The domain model contains all relevant knowledge regarding the established factors applicable to the learning environment being used, including the properties of objects, ontology, rules applied, available interactions, transformations, and other details which in their combined overall context completely describe the educational content available in this space. Additional objects and facts can be added so that the learning environment can be further enriched with the new content. Once the learning environment is completely described, it is then possible to define the skills that will be acquired within the specified course. Each of the skills to be mastered will be represented by several steps associated with the selected pedagogical model. For example, in case of the NTC pedagogical model, a step can be an association, action, or gamification, while in the classical pedagogical model, this can be presentable information, a question, and an answer. Each of these steps can be further expanded into their basic building blocks, which describe in detail the exact sequence of learning progress, accounting for the personalization aspects. The personalization aspects rely on the processing of the observed parameters described before using AI algorithms, and the resulting actions represent the decisions associated with the selected pedagogical strategy. Therefore, the topology of the flowchart is directly connected with the chosen pedagogical model and the associated strategy. The sequence of steps within each of the skills can be edited on both representation levels, namely, a pedagogical and detailed representation. Each pedagogical step is envisaged as a template, which can help teachers adapt it to the exact requirements needed within a course. This aspect of the authoring process is particularly innovative when compared to existing authoring tools, as it dramatically reduces the effort required to create a learning strategy. In this prototype, a chemistry course is shown, where students or children aged 7 to 11 can learn different aspects of basic chemistry, including atom structure, electrons, protons, neutrons, energy levels, the periodic table, and equation balancing. Two different pedagogical models are shown, and in the NTC, the focus is on providing gamification and association elements within the learning process. The students need to complete certain actions using the game-style approach. The system is continuously monitoring the learning progress, and appropriate actions are taken by the pedagogy agent, providing more content or changing the type of the media type used when deemed necessary.